We're going to start this just looking at some motion that we've talked about a few times already. Simple idea, you take a ball, you toss it into the air. What's the displacement versus time graph look like? Could you do that again? I only saw half of it. All right, excellent. So it's an upside down parabola. So if I have displacement and I've got time, my graph should look something like that. Okay? Thinking back to geometry, what is the equation for a parabola? What is the general format of an equation for a parabola? Mark? Nice. I thought it was plus C equals Y. You did really good on the first part. I didn't remember it initially. So ax squared plus bx plus c equals y. Good. Let's take a look here and identify a little bit more about what each of these is physically representing. Mathematically, we understand that x and y are coordinates on a coordinate plane. But in terms of physics, in terms of the real world, what are they representing for us? What is x representing? Time. So x is time. What's y going to be? Distance from origin, or displacement if we're being specific. So x or y is displacement. And I'm just going to list behind these the variables we're going to use. Time, t, and displacement, delta x. Okay, what is c in terms of a parabola? Say again? I don't think you were wrong. I just didn't entirely hear you. Right, starting point, so, or typically the y-intercept, right? It's the amount that you've raised the parabola up or down. So we're not actually going to worry about c. So we're going to ignore that one because mathematicians really like to be able to have x and y shift so they can move the graph all over the place and move the parabola up into really ridiculous locations. In physics, we look at you and say, why? Why not just place your sensor and call 0 a convenient location? So we're going to place 0 where it's convenient for us every time so that there's never a c value. Sound good? All right, so we're going to ignore c. B. Well, if x is t and y is change in x, that means we've got an equation that says something times t is change in position. We've seen this equation. What is it? What is this last variable? We've seen this equation. What is this variable? If you're not sure, flip back a page in your notes. You should be able to see it. Anybody find it? Excellent, velocity. So B must then be the velocity at the start of our motion. Velocity at time equals 0. And to shorten that, we are going to call it V naught, or V sub 0, where 0 is just telling us velocity at time equals 0. Okay? And then lastly, A is actually going to be our acceleration. Is acceleration. There. And then after I go through and I swap these out, there's one small difference that I have to make. I'm not going to spend the time to go through the derivation to prove it because I hate wasting time on a lot of derivations. So we wind up with change in x is equal to, we got rid of c, v naught t plus 1/2 a t squared. This equation is basically the same as our parabola equation, We've just swapped in a constant here to show a little bit of the relationship for the actual acceleration. We've gotten rid of this constant, so we'll say we always start here, because why would we start anywhere else? And this is the first of a set of 4 equations that we call the kinematics. The other ones that we follow in here are delta x is equal to half v plus v naught, where v is a final velocity or a velocity at a later time. V naught is still our original velocity times t. V squared equals v naught squared plus 2a delta x. And v equals v naught plus at. Again, as a set, these are what we call the kinematic equations, which are basically just a set of equations that describe accelerated motion. Equations that describe accelerated motion. Okay? Questions at this point? So far, so good? Okay. So really what we're giving you is a set of tools that you can use to try to solve different problems, to try to understand and explain how things move under set parameters. These equations are only useful for constant acceleration. Anytime an acceleration changes, we have to break problems into parts. These can't describe situations where the acceleration changes. Only describe constant acceleration. If we have a changing acceleration, we have what we call a jerk, and we can't deal with it at this level. And that's actually what it's called when acceleration changes, is jerk. Okay, so let's go ahead and we're just going to take a look at an example problem, and let's just stick with the rubber band ball being tossed into the air. So whenever we're approaching a physics problem, I don't care if it's a 9th grade physical science problem or if it's junior level quantum mechanics, the same approach to solving the problem always works. And a mnemonic device that I put together to make sure that we have this place to start is DICES. So this is just a problem-solving strategy that I'm going to teach you because I've found it works. I've used this when tutoring literally college-level quantum mechanics students and 9th graders, and it doesn't matter what level, it helps us figure out what do I need to do first. First is draw. Maybe this is graphs, maybe this is free body diagrams, doesn't really matter. Free body diagrams. Graphs. But the purpose behind draw is so that if there's more than one of us working on a problem, we've got something common to understand. We can all look at the same problem and we understand where we're talking about, what's going on, and we've got the same picture. Identify. Simply identify constants and variables that you know. Constants and variables. C, convert. If necessary. This one's pretty self-explanatory. You can't solve a problem if you're in different units. E, equation. Pick one. Pick one that helps. And S for solve. Do math. So anytime you're working a problem in this class, or really it works out in other classes too, these are the steps I suggest you follow. No, I don't require that you follow them, but if you're going to raise your hand and ask me how to do a problem, I'm going to ask first, well, have you drawn it out? If so, well, what variables have you identified? And I'm going to go through these steps because when I do a problem, it's how I solve it. So I do encourage using this. It may seem a little trivial with our starting content, But getting in the habit of using this tool helps out a lot for when we get to the stuff that's actually challenging for you. It gives you a starting point, gives you a way to make sure that you're not just freezing up on it. So let's go ahead and use this. Example 1. So we said that we took a ball and we tossed it into the air. Now let's say we toss it exactly a meter. The ball is tossed 1 meter into the air. In order to reach that height, what speed was it thrown at? At what speed was it thrown? Okay. So starting this problem, I'm just going to start with draw. Oh, hey, look, I've drawn it. Plotted a displacement versus time graph for this motion. Okay, that's all we're looking for. I mean, I can identify this is right here. It's where it leaves my hand. This is the max height. This is where it returns to the hand, but that's really all extra. Okay, after I've made my drawing, my next step is identify. I'm going to list out any variables that I could possibly use. Since we're talking one-dimensional motion, I know that those variables are initial velocity, final velocity, acceleration, change in position, and time. The ones that just appeared in our equations. So V naught, V, A, delta X, T. What ones do I know? What values do I know? How much? For initial velocity? We're trying to find what speed it was thrown at. So that one can't be 0 because if I threw it at 0, it didn't go anywhere. Somebody else, another different one that we might know. Delta X, how much? Got to be 1 meter because that's how high it goes. Okay. Acceleration, how much? Good. So gravity, negative 9.8 meters per second squared. If we are talking about a falling object, gravity is always 9.8 meters per second squared because you are on Earth. If you are not on Earth, we will let you know. Okay? We need at least one more. All those kinematics have 4 variables. We need at least 3 in order to solve. So what other value can we figure out? It's either going to be V or T. What other value could I possibly know? How could I figure out T? But I don't know that time. Other thoughts? Is there a velocity or a time that I could know? Which one? Why V0? He's right. At the very top, what's the slope? 0. And the slope of a displacement versus time graph is velocity, right? So that value has to be 0. 0 meters per second because the slope is 0 at this location, which is kind of why graphing it was a helpful step. So the drawing piece wasn't completely useless. All right, so now I've got my values. They're all in meters or seconds, so I don't need to do any converting. Picking an equation, I want something with V, A, delta X, and V naught. That would be V squared equals V naught squared plus 2A delta X. So from here, I'm just going to plug in my values. V squared, 0 squared equals V naught squared plus 2, negative 9.8 times 1. If you get to here on a test question, all of my free response test questions are typically 2 or 3 points. If you can get this far, you've earned 1.5 out of 2 or 2.5 out of 3, just for getting to that. It is technically possible to pass my tests without ever actually putting down the right answer, but having put out correct physics. Everything after this point is just math. And I'm not always interested in seeing what your math can do, but I am interested in seeing what your physics can do, so it's the majority of the points. So from here, I'm just going to solve 2 times negative 9.8 is negative 19.6. Negative 19.6, v naught squared equals 0 squared. Add this to the other side, take the square root, equals v naught. Questions about how we got here? Okay, so I can solve that and find this is 4.43 meters per second. How do people feel about that one? Okay, let's try one more then. Example 2. A drag racer capable of accelerating at, let's go 60 meters per second squared, completes a 1 kilometer race. Let's say we want to know how long did it take them if they started from rest. If he started from rest. All right, I'd like you to take a moment, go through those DICE steps, sketch out a displacement versus time graph for draw, identify what variables you can, get as far as convert, and then we're going to come back and see how you guys did. So to start, I'm going to plot out a displacement versus time graph, mostly because I want to call back to our daily question here. And our daily question said, what should you do in order to, or how do you know if an object is accelerating from a displacement versus time graph? How do you know an object is accelerating from displacement versus time graph? It's curved. This one's curved up. If it was curved flat, that would mean it was slowing down. But a drag racer speeds up as the race is going on, so we should have this curved up, showing that the slope gets steeper. This is time. All right, variable identification. V naught, A, delta X, T. What ones did you know? A, how much? Good. What else? V naught, how much? 0. One more? Delta X, how much? 1 kilometer. Draw, identify, convert. Do I need to convert? Okay, this is 1,000 meters. Equation. What am I trying to find? I'm trying to find time. So I need V naught, A, delta X, and T. That says to me delta X equals V naught T plus 1/2 AT squared. I picked that equation because it doesn't have V. I don't know V. I don't care about V, so pick the equation that doesn't have a V. Make sense? Plug things in. 1,000 equals V naught. Well, this whole thing is 0 plus 1/2 60 T squared. So 1,000, this is going to be 30. 1,000 over 30 equals T squared. Square root of 100 over 3 equals T. So, like square root of 33, what is that? Like 5 point something? 5.7, so 5.8? Okay. 5.8 seconds. Okay. How many people had the right variables identified? Okay, good. So, questions about any part of this problem? How many people feel okay with this? Like, hey, I can actually do that. So a few of us. All right. So what we're going to do today for the rest of the hour is we're just going to practice these. And actually, that's what we're going to do tomorrow. On your daily planner, I've got listed practice problem sets A, B, C, D, E, F. George, before you go, practice problem sets A, B, C. Pick 3 problems out of each. Okay? And that's what I'm going to ask the rest of us to do during the rest of this period, is just pick through practice problem sets A, B, C, 3 problems apiece out of them. Practice problem set A is on page 44. They usually look like this kind of box. They always put the easiest questions at the top and the hardest questions at the bottom. If you're struggling with them, do the top 3. If you get the first one, no problem. Maybe skip down a little bit, try some of the bottom problems. I'm asking you to do practice problem sets A, B, and C today. We're going to go over them in class tomorrow, and then we're going to tackle practice problem sets D, E, F. Right? I'm going to leave this up front, so it's got an answer key, answers are posted here. Yes, you are allowed to come up and write down the answers so you can just check them as you go. This is a tool for you to use to see, do I know what I'm doing? Okay? Questions about what I'm asking you to do? Okay, go for it. Yeah. You asked another question earlier. Did I get it? Okay. Let me address that real quick. Hey guys, quick question that was asked. Are we going to get these equations on tests and quizzes, that kind of stuff? So, when I took physics in high school and college, they made me memorize equations. That was miserable and a waste of my time. And in the last 5 years, College Board has also started to agree with that. And so none of the physics classes in this building or this district require you to memorize equations because it's a waste of your time. All equations will always be written on the board up here and provided for you on all tests and quizzes. You are required to know what the variables stand for and when to use equations, but you don't need to memorize the equation itself. Good?